Right. Ready? So good morning all of you. The summary of the last lecture is not there. We are going to start a new summary. Right. Now take a fresh page and put the heading solid state of physics. Solid state physics. Right. So what is this solid state physics? A condenser matter physics. What we are going to discuss here. Now let us suppose I have given this to you. That means this is a material. I have given this material to you and I ask, what is this material? What you will do? You will say plastic. Huh? What you will do? An unknown material. They say everybody know plastic material. So some unknown material I find. Okay. So just I have given to you until I ask what kind of material is. What you will do? Properties. First we will study the properties of the material. What kind of properties you will study? Mechanical property, which is very useful for the manufacturer. The manufacturer will design the shape. For that he will follow the physical properties of the material. Is that clear? Next one, electrical properties. Next one, chemical properties. Next one, thermal properties. Next one, magnetic properties. Next one, optical properties. These many properties you have to study. Okay. For example, I have given two things, a quartz and a diamond. I have given to you both. I ask you to separate quartz and diamond. Maybe generally, do you think quartz and diamond both are same? But both are colorless. Seems to be same, but both are different. How you will separate those two? Based on? What? What character? See, if you see the physical properties first, diamond is harder than quartz. Quartz is a soft material. Diamond is a hard. That means you are separating the material by using a mechanical properties or physical properties, whatever it is. Next, if you see one more thing, diamond is a 4 phases, quartz is a 6 phases. And chemical composition, if you come to the chemical composition, diamond is what? Carbon, C. Quartz is what? Silicon dioxide, SiO2. Where you use quartz material? Watches, computers, that computer boards, chips, everything somewhere. And diamonds you know very well. Okay, so good. Right, anyhow, so whenever any material is given to you, first we will study the properties of the material and we will note down and we will compare that properties with already prepared, already some charts will be prepared. Already we have done earlier study. Just we will compare with those properties and we will come to the conclusion, this is this material and this is this material. Am I right? Good. Now ready. So what is this solid state physics? This is the study of periodic systems, and what we are going to study here, periodic systems are nearly periodic. Study of periodic systems or nearly periodic systems in thermodynamic limit. What is this thermodynamic limit? For example, if you consider this material, can you say how many atoms are there? No. You can say that is the thermodynamic limit. Thermodynamic limit will say how many atoms or molecules exist per cc. That is called a thermodynamic limit. Okay. So what is this thermodynamic limit? The thermodynamic limit means this is nearly around 10 to the power of 21 atoms per cc. 10 to the power of 21 atoms per cc. Okay. Now I have given a material to you. So now you have to study what? 10 to the power of 21 atoms characteristics per cc. Is it possible for you? No. So then it was a very difficult task. It seems to be very difficult task in the beginning. But luckily God always help human beings, but human beings are not ready to take it. So what happened at first it seems to be very difficult to study such a large systems. It's not a joke actually. 10 to the power of 21 atoms means even you can't count also those many number of atoms. It's difficult to study such a large systems. For example, if you see, okay, some atoms are there. Let us consider a Z atomic number of the material whatever you are taking. Let us take silicon only. How many electrons are there in silicon? 14. So each atom contains 14 electrons, and those 14 electrons are interacting with another 14 electrons of the another silicon. Like that, how many electrons interactions you have to study? So initially they thought that, oh, this is not possible, God, it's very difficult to study such a type of large systems. But two important properties of solids made this study easy. So made this study easy. What are those properties? Let us start. Let us discuss that also. Basic, very basic. So the first one is translational invariance of the solid. Okay. Translational invariance of the solid. And sir, what is this? What is the meaning of this translational invariance of a solid? Wait a minute. For example, if you see this board, around 16 feet is there. Okay, so it's a large system. It is made up of some material. So in that material, what you are having? Atoms, molecules, atoms combined together, and we got a material, solid material. Now I want to study the properties of this. No need to study the total material. This solid is having a property called translational invariance. Means if you take a part, that part will be repeated somewhere, and it is having a translational invariance, means whatever the properties this part is having, the same properties exist everywhere. That's why, Bhaiya, no need to bother about that 10 to the power of 21 atoms. Just take a part of the solid and study. The same properties exist for everywhere in the solid. That is called translational invariance of the solid. Wait a minute. So here, for example, you have taken a solid. And here I am taking some part like this, just like this I am taking. If you observe carefully, some pattern, same pattern is repeating. If you observe carefully, some same pattern is repeating. Something like this. So you need not to bother about the total solid. Just take a part of the solid. That means it is enough. It is enough to study. It is enough to study the properties of a part of the solid. Only a part of the solid you please study. The remaining things no need to study. That's good. No need to worry about all the people. Just study about one student, and the same properties exist for everyone. Okay. What is that part called? We are studying only a part of the solid. What is that part called? Unit cell we call it in 3 dimension. In 2 dimension what you call? Motif. What is that? Motif. So this is called motif. In 2 dimension we call it as a motif, and in 3 dimension we call it as a unit cell. Earlier, that means in the beginning of the crystallography, but nowadays everyone is using the word unit cell. But the strictly variation is a motif for a 2 dimensional, and is it clear? That's good. If you take a bed sheet, if you see some bed sheet or cloth, whatever it may be, some pattern will be repeated if you observe carefully. So that pattern which is repeating itself is nothing but what? A motif in case of 2 dimension. In case of 3 dimension, generally we call it as a unit cell. But nowadays modern crystallographers using the word unit cell for both 2D and 3D. That's why you forgot this word. That's good. So I hope you understand the first point clear, and the second point. Earlier I said I have given some material, let us say silicon, it contains, it is having 14 electrons. So these 14 electrons are interacting with another 14 electrons of the silicon. Then how to study? It's difficult now. Writing the Schrodinger equation for one electron, it is taken 25 years to understand. What Schrodinger equation? Hydrogen atom, how many electrons? 1 electron. The 14 electrons, how I will write the Schrodinger equation and how I will solve? The only one mechanics is quantum mechanics. The only equation is Schrodinger's equation available. How I will solve? Don't worry. The second one, behavior of core electrons. Oh, just wait. Now here I am assuming this is the atom. Of course, it's a nucleus. The nucleus contains shells. Atom contains the shells around the nucleus. Here we are having electrons, and here also we have electrons. The electrons which are very close to the nucleus are called core electrons. These are core electrons. Unfortunately, these core electrons are not participating in the bonding. Why they are not participating? You should know the reason. Why they are not participating? Simple. These core electrons are tightly bound to the nucleus or ion core, you can say. So these core electrons are tightly bound to the positive ion core. That's why they neglect the dynamics of these core electrons. We neglected dynamics. That's why you need not to bother about that 14. Just see how many valence electrons are there. Those valence electrons will participate in the bonding. So these electrons are called valence electrons. And these electrons are participating in bonding. So what is happening here? Maybe in your lower classes, maybe your school teachers or college teachers explain how we will get a material. Generally we will say it's a combination of molecules, and molecules contains atoms or something like that. So whenever a molecule is formed means what? 2 atoms are combined. Say yes or no? For example, this is some material. Okay. Now the 2 atoms are coming close together and combining. On what basis they will come close together? There exists attractive force. So this is the material which contains some atoms, and now they are coming close together with the help of attractive force. Okay. You can ask one thing. If they are coming close together and attractive forces are there, then it will become a point object. But we are not having any point object here. We are having a well defined shape of a solid. Then what's happening there? Whenever 2 atoms are coming close together with the help of attractive force, then the valence electrons are also coming close to each other. Am I right? The valence electrons in this atom, the valence electrons in this atom whenever they come close together, what will happen? The shells will keep on repelling with each other. The electrons and here and the electrons in this atom will repel with each other. And there exists a repulsive force. And the system will attain equilibrium. Equilibrium, I hope you know what is the meaning of equilibrium. The attractive force and the repulsive force both will be the same. Like that, we are getting a material. So, in this solid, we have two types of forces. One is attractive as well as so for a far distance, attractive is dominant. For a small distance, as you are coming close to together, then repulsive force will be dominant. Say yes or no? Okay. So, if you want to see the graph, see carefully. This is R, means a separation between the atoms, and this is the force. And I am taking this is the equilibrium position. Okay. So, the attractive force will be, this is the curve. Okay. And the repulsive force will be like this. Something like this. And the resultant force will be for large distance, which force is dominant? For for small distance, which force is dominant? Repulsive. That's why your net force will be, if anybody asks to draw the graph, you should draw like this. But as it approaches the equilibrium, the dominant force is what? Repulsive. That's why the net force graph will be like this. As it comes close together, repulsive is dominant. As it is very far away, attractive is dominant. Is that clear? But if you draw potential energy curve, it's ulta. Attractive become repulsive become, and this curve is also little bit ulta. The reverse, the reason is F equal to minus dou U by dou R. That is the reason. That's why the curves will be reverse. I hope you understand here what I am explaining. Come on, write down. So finally we understand two things. You need not to bother about the total crystal, only just bother about a part of the solid. That part of the solid is nothing but the unit cell. And the core electrons are tightly bound to the ion cores. That's why we neglected the dynamics. That's nice. Only valence electrons are participating in the bonding. This is how the bonding is. How many types? What are the types of bondings you have? Ionic bond, covalent bond, metallic bond. That means overlapping of shells, SPDF shells. In chemistry you studied sp hybridization, sp2 hybridization, all these things are chemistry you studied. That is nothing but the overlapping of shells, which are reason for these bonds. I think you can't see that board, am I right? Original board, because this light will fall on that. You people can't see that side, I think. You will see here. I told you to write in a single notebook. From the back side you can write SSP. Tomorrow we will start spectroscopy, where the nuclear physics end. From there you will start spectroscopy. Don't maintain a separate notebooks. Nuclear physics notebook, no pages. Oh. Spectroscopy, right. Whenever two atoms are separated by a large distance, attractive force is dominant, and whenever they are coming close together, and at once it reaches the equilibrium separation, both the forces are same. So equilibrium separation, that is R naught. Okay, so then magnitude of attractive and repulsive both are same. That is called equilibrium. Like that, the valence electrons are participating in the bonding. So that one we are not discussing here. That chemical properties we are not having in the syllabus. That is quite different. Over. Are you ready? Right. Now come to this next one. Types of solids. How many types of solids you have? The first one, crystalline solids and non-crystalline solids. Non-crystalline solids. And again crystalline is divided into two types. One is a single crystalline another is a polycrystalline, single crystalline. Can you give one example for a single crystalline? Quartz, quartz as well as diamond also, diamond. But a polycrystalline, polycrystalline, so if you take a copper, silver, RS, RS means gold, gold. So all these are polycrystalline. Okay. So sir, first of all, what is meant by crystalline? The crystalline substance are having regular and periodic arrangements. Periodic arrangement of what? Of atoms. And a non-crystalline, here we are having, I hope you understand, irregular arrangement or a random is the correct word, random arrangement of atoms. Can you please give examples for this non-crystalline? Plastic, glass, all these are non-crystalline. Okay, that's it. Yeah, come on, right up. Next we will start with the crystallography. So it's very, very important to understand the properties of solids. We have to study first crystallography. My advice, immediately read the book. See, because we can't write each and everything in the notebook. If you read the notebook, then you will understand clearly. Now sound is okay? So types of solids, we have crystalline and a non-crystalline. Crystalline again a single as well as a polycrystalline, and non-crystalline, those are amorphous, what you will say? Amorphous. Glass, plastic, amorphous solids. Right. Now ready. So crystal. So here we are going to start the crystallography, Babu, which is very, 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 very important. If you understand crystallography, then only you will understand X-ray diffraction. Otherwise, no. Okay. So listen. Crystal. Could you please tell me what is meant by crystal? Lattice plus basis. Lattice plus basis. We will come to this basis part later. First, let us concentrate on lattice first. So now, lattice. What is meant by lattice? I am explaining from the basics. If you know already, it's okay. Otherwise, listen. Lattice. It is an infinite array of points. Okay. How you are getting points? Someone is creating na. Randomly you cannot place na. Because it is a periodic arrangement. It is a regular arrangement. So somebody is creating. Who is creating? Translation vector. Right. An infinite array of points obtained by, wait a minute, obtained by translational vector. Translation vector. Okay. So wait a minute. What is this, a translation vector? The translation vector, this is the T bar, which is it is having a, 2 dimension as well as a 3 dimension. In 2 dimension, we will write this translation vector as T bar equal to N1 A bar plus N2 B bar, where A bar and B bar are called primitive lattice vectors or simply primitive vectors. And this is the T bar in 3 dimension, that is N1 A bar plus N2 B bar plus N3 C bar. So here we call this A, B, C are primitive vectors, N1, N2, N3 are called integers. What are these, ma? Integers. And A bar, B bar, C bar, these are called primitive vectors. Primitive vectors. Okay. So generally this T bar is represented by T N1 N2 or T N1 N2 N3. If it is a 2 dimension or 3 dimension, it depends. Now how we will get the points? I will explain a small example. Are you listening? Now let us suppose, all of you please see the board. This is my origin, 0, 0. Now I am placing this point, okay, and one more point here. Let us suppose this is a primitive vector A bar. First we have to define a primitive vector. Next I am defining another primitive vector B bar. Now with the help of these 2 primitive vectors, I am going to get all the points in the space. For example, I want to get this point. So I am taking a translation vector. I hope you are observing. This translation vector is nothing but how many A's? 1. How many B's? That's why A bar plus B bar. Still not understanding. I want to get this point. Okay. And I will use another translation vector to get this point. So how I will get this vector? By the translation vector, how many A? 2A bar plus 1B bar. Because this is what? 1B. A. Is it okay? Right. So something like this. It's a keep on, we can place the points like this. So all these points will be obtained with the help of translation vector. Whether you are in the 2 dimension or 3 dimension, it depends. For example, if you are in a 2 dimension, this is the x-axis and y, and this is, okay, I think I need not to, yeah, it's okay, 1 minute. If it is a 2 dimension, we can take the example of a square lattice or a rectangular lattice. This is a bar and this is a B bar and this is a gamma. So we can say here A bar and B bar are primitive vectors, okay. And if you talk about the 3 dimension, you can say like this, listen carefully. I can take simple cubic and I can say this is A bar and this is B bar, something like this. This is a C bar, and A bar and B bar and C bar are primitive vectors. With the help of those 3 primitive vectors, we will construct the remaining all lattice points. Is that clear? So finally, what is meant by crystal? What is a lattice? Just arrangement, infinite array of points. How you are getting that points? By translation vector, either 2 dimension or 3 dimension. Is that clear? But remember, these translation vectors form a group. Translation vectors, all translation vectors form a group. Group means, I hope you know, closure, associative, identity, inverse, something like that. Okay, all those properties are satisfied, that will be a group. And the next one, all crystals, the lattice, I am talking about the lattice here. Lattice is invariant under translation. This is what we said in the beginning. Translational invariance of the solid. because that property is here for lattice. The lattice is invariant under translation. 2 points I said about this translation vector. First one, translational vectors form a group. Next one, lattice. Lattice is invariant under. Write those 2 points later. Come on. Lattice is invariant under translation, under translational operation. These are the 2 points. I think 1 more week we have high temperatures. After that, slowly it will decrease. Ready? Yeah? So that's it. So crystal means simply combination of lattice and basis, and first we have given a definition for lattice. It's a simply arrangement of points, infinite arrangement of points infinitely, and that arrangement is done by translation vector, and the translation vector forms a group, and the next one under translation lattice is invariant. That's good. Now ready. Okay boss. Then what about rotations? Rotational symmetries. So let us discuss that. Are you ready? To understand these rotations, I am taking a small task. All of you, listen please, very important. Now here, I am taking a lattice point A and another lattice point B. And these two are separated by some distance. We call it as a lattice parameter. Let us say it is A. So A and B are two lattice points separated by a distance A. Now what I am doing is, listen carefully. Now this is AB line. I am standing at A, okay. I am rotating this scale like this. That means this point will come here. Say yes or no? Now I am doing rotation because I have to discuss the rotational symmetry. So what kind of rotational symmetries exist? 1 folder, 2 folder, 3 folder, 4 folder, 5 folder I want to discuss. That's why I have taken the lattice vector, and now I am at A and I rotate this up to an angle alpha. What angle? Alpha. Okay. Now I rotated through an angle alpha like this. So this is the point B, now you are getting here. That's why I am taking it as B prime. Similarly, one more thing I am taking. Now I am at B and rotating this vector through an angle alpha. Then we got the some point here somewhere, and this point is nothing but what? A prime. Say yes or no? Cool. Now one thing observe. If this is A, this is also A, and this is A because this is also A, same. Because the same vector we rotated like this and like this through an angle alpha. Alpha. Cool. Okay, so now I am taking just a perpendicular, that means like this, and here also I am taking a perpendicular. You know this angle is what? 90. Then this angle is total is alpha. This is 90. That's why alpha minus. Similarly, this is 90. So this angle is nothing but alpha minus pi by 2. Now I am joining these 2 points, that A prime and B prime. So one thing is very clear. If this is A, this is also A. Now come to this. Hypotenuse is A, angle is alpha minus pi by 2. That's why this is nothing but A sine alpha minus. Is it opposite side or adjacent side? That's why sine. Everybody understand? Now, similarly, this is the hypotenuse. This is the opposite side. That's why A sine alpha minus pi by 2. Okay. I think I can write this as a minus A cos alpha. I can write this minus A cos alpha. Any doubt? Now just I am writing this B prime A prime. B prime A prime. Just I am taking how much distance it is. That means I am taking magnitude. This is A and this is minus A minus A. How much? A minus 2A cos alpha. Am I everybody understand why sin alpha minus pi by 2 is minus cos alpha? Good. So this is nothing but A common. 1 minus 2 cos alpha. This is what I get from the geometry. Okay. Now let us suppose this A prime and B prime are also valid lattice points. That means those points are also obtained by translation vector. Say yes or no? Then definitely this entire magnitude must be integer times A. I said A is the lattice parameter. I hope you are understanding, I hope. I said earlier lattice parameter is A. So everywhere what I have to do? 2A, 3A, 4A, 5A like that. So here if you assume this A prime and B prime are also valid lattice points, then also they must represent a lattice vector whose magnitude is an integer times A. Then only they are valid, otherwise no. Okay, one second. If A prime and B prime are valid lattice points, then I hope you understand what I am saying. B prime, A prime magnitude must be equal to an integer times. But I already find from the geometry how much it is. A 1 minus cos alpha, 2 cos alpha equal to AA gets. That implies cos alpha equal to 1 minus P by 2. Check, sometimes I will do mistake. So cos alpha equal to 1 minus P by 2. Good. Okay. Now come to this boss. Now I am taking a P value, next cos alpha, because my cos alpha equal to 1 minus P by 2. And after that I will get alpha. Okay. Then after that I will define a fold. I will define the fold. 1 fold, 2 fold, 3 fold. I will tell you what is that. Don't get tension. Are you ready? One thing is very clear. Cos alpha value line between plus 1 and that one you know. It always line between minus 1 to plus 1. Now I am taking P minus 1. Just I taken minus 1 because I know that's why I have taken minus 1. You can try minus 2 also. It is not valid. Check. If I take P equal to minus 2, 1 minus of minus 2 by 2, 3 by 2. Is it valid? That's why directly I have taken minus 1. Okay na? 1 minus of minus. Say. Right. Now I am taking P0. If P0, good. Next I am taking a P1. Good. I am taking 2. I am taking 3. Minus. Shall I take 4? No. Because the cos theta line between plus 1 and minus. Or only these values allowed. Yes, let us see what you will get. Are you understanding? Now cos alpha is 1. That's why alpha 0 r. Next pi by 2. 1 by 2. Pi by 6 or 3 ah? 3 plus or minus. Because it's a cos. Either anti-clock or clock. Next 0 plus or minus. Minus 1 by 2. 2 pi by cos 120. Next minus 1. Good. Now the fold is defined as 2 pi by alpha. 2 pi by alpha. Now the first one. Here take 2 pi. Don't take 0 ma. 2 pi by 2 pi. Answer. Next. Ready. 2 pi by 3. Endu tension padtaru. 2 pi by 2. Next 2 pi by 2 pi by 3. Next 2 pi by pi. So one fold exists. Means take a solid or a crystal. Okay. If you rotate this through 360 degrees. 360 degrees. And one rotation of 360 will give you the same side. That is called fold symmetry. One fold symmetry. Next one. 6 fold. That means if you take this crystal and you have to see the axis, different axis. Axes are not always the same. You have to keep on change the axis. If you are having any doubt, just go and type rotational symmetric axis of a crystal. Total how many rotational symmetries are there? Triad, dyad, quad, something will be there. So I don't remember. If you want, you just go through that any Google or something like that. Reason. Next, what is this six fold? That means if you rotate 6 times through an angle pi by 3, you will get the same side. Next one, what is this fold? 4 fold. So if you rotate 4 times through an angle 90 degrees, this we can show here easily. So please see, okay, 90, 190, 290, 390, 490. Understand? The remaining axis I can't, okay. So I think this type of rotations will be there, 2 pi by 3, pi by 3 like this, okay. So this is easy to show that, okay. Next, this is the 3 fold. What angle? 120 degrees. If you rotate 120 degrees 3 times, you will get the same side. And this is also a 2 fold. What angle? Pi. That is obvious, you know that. So 1 fold, yes, present. 2 fold, present. 3 fold, present. 4 fold, 6 fold. Kahan gaya 5 fold? Does not exist. 5 fold symmetry in the crystal does not exist. Where it exists? Quasi crystals. I don't know what is quasi crystal, but that 5 fold symmetry exists in quasi crystal. In crystals, we don't get any 5 fold symmetry. Everybody understand this? Come on. Conclusion. Just type rotational symmetries in solids, crystals. You will get that dyad, triad. Triad means 3 times, dyad means 2 times, something like that. Conclusion. 5 fold symmetry. Do it yourself, no need to copy. It's a simple 6th class geometry. 5 fold symmetry does not exist in crystals. At 5 fold symmetry exists in quasi crystals. Unfortunately, I don't know much about quasi crystals. Generally, quasi word is used in physics for slow variation. Slow variation, something like that. I don't know here what sense they used. You know, thermodynamics is quasi-static process. That's what I'm saying. All are zero. No variation in energy, no variation in internal energy, no variation in the work done. Quasi-static process, which varies slowly. Here the meaning, I don't know. If you are interested, please check. So 5 fold symmetry does not exist in crystals. If anybody asks you to show that, you just take a small geometry and you can prove this. think total symmetry is 23. Out of that, point symmetries and rotational symmetries are the axial symmetries, like that will be there. Total symmetries are 23, I think. 22, 20, I think 23. Oh, I remember like that. Or 21, 22, around 21, 14. Right. Babu, off that light. Ready? So, final conclusion. So, in crystals we do not have 5-fold symmetry. That means if you rotate 5 times through any angle, you will not get the same side or same pattern, whatever it is. Ready, boys? Now, okay, fine. Once again, crystal. So, what is meant by crystal? Already given, lattice plus basis. We have already given what is meant by lattice. One second. It is a simply array of points. Array of points. Babu, listen please. Just I am taking some arrangement of points like this, and I can say this is what? Lattice. Now come to basis. What is meant by basis? In this classroom, you have lattice or benches. You are all what? Basis. You are the atoms or molecules, whatever it is. So, basis means atoms, a group of, atoms, okay, atoms or molecules or ions, anything you can take, atoms or molecules or ions. But remember, which are identical, in, don't simply say atoms are basis, molecules are basis, ions are basis. If you want to say that it is a basis, you can take a group of atoms or molecules or ions, but which are identical in composition and orientation and that's it, composition and orientation, something like that. So, they should be similar in some properties. We should not simply take whatever you want, understand, that only called basis. We can say this is a group of atoms or molecules or ions which are identical in composition or orientation. Wait a minute. Now I am taking plus, this is the basis I am taking. Then if you combine this, what you will get? So earlier lattice and at each lattice point we have atom. At each lattice point we have atom. So then it become what? A crystal. That's it. So crystal means a simply combination of lattice and base. Okay. Now let us start some basic concepts. First one, unit cell. Unit cell. If you see the flooring, your flooring, okay, flooring there, okay. So what you are having? Tiles. This total flooring, let us say it's a solid. How you got that entire solid? By placing one tile. One tile, you have taken one tile, square tile or rectangle tile, whatever it may be. So you have taken that tile and you are keep on placing that. Then you got the entire solid. That part of the solid by which we will get the entire crystal by translational repetition is called unit cell. A part of the solid by which we will get the entire solid by translational repetition, because you are translationally repeating. Is it clear? Whenever you are saying the definition, it should a proper way. Don't say simply unit cell means a part of the solid. What a part of solid? It should be repeated translationally, then you have to get the entire solid. Be careful. So a part, some people will say volume also, of a solid by which we get the entire crystal or solid by translational repetition. Translational repetition. That's good, that's good. Okay, that is nothing but unit cell. For example, you can say, example if you want, you can say in 2 dimension I am taking. This is the part I have taken. Now if you keep on placing the same part, everywhere, so you will get this entire solid. So this is the translationally repeating. Wait a minute. This is X and Y, 2 dimension. If you see in the 3 dimension, you have, I can take a simple cubic, something like this. Okay, now I am repeating this is in the space. Now I am repeating this in the space. Like this. It's a keep on, you can build up the entire solid by simply repeating translationally. So here this is called unit cell, and here this is also called unit cell. Actually motif, but we are saying modern crystallographers are saying unit cell only, no issue at all. Next, second one, primitive cell. Primitive cell. So what is meant by primitive cell? You have unit cell, you understand unit cell. It's simply a part of the solid. By translationally repeating, we are getting the entire solid. Then what about the primitive cell? Primitive cell is a unit cell, no doubt. Primitive cell is a unit cell, but which is having minimum volume. That's it. So primitive cell means minimum volume unit cell. What is the primitive cell? It's a unit cell which is having a minimum volume. How it is having a minimum volume? It is having only one lattice point per unit cell. That's why it is having a minimum volume. Understand? How it gain minimum volume? Because it contains only one lattice point. Only one lattice point per unit cell. So that is called primitive cell. I hope you understand the definitions. Unit cell means simply a part of the solid. By translational repetition, we will get the entire solid. Primitive cell, it's a unit cell with minimum volume. Why it gain minimum volume? Because it contains one lattice point per unit cell. Oh, in unit cell you can have more than one point per, yes, 1, 2, 4, you know, simple cubic, BCC, FCC, something like that. Come on, write down. Next one is very crucial discussion. Just participate in the discussion. We are repeating this translationally, that's why we are getting entire crystal, that's why it is unit cell. We are repeating this translationally, we are getting entire crystal, that's why it is called a unit cell. The primitive cell is a minimum volume unit cell. Why the volume is minimum means it contains only one lattice points per unit cell. So if any unit cell is having more than one lattice point per unit cell, it is not at all primitive. Now we have taken 4 structures there. I hope some of you know simple cubic, BCC, FCC, and the last one is what? Base centered. In base centered, AB is not equal, A, B, C not equal. That's why we have to draw like this. Simple cubic, BCC, FCC, ABC are same, but this base centered, ABC are not same. And A length, B length, C length not same. Matchbox. Matchbox is A is not equal to B is not equal to C. Ready? Is it over? Now listen, 1 minute, just wait. Up to primitive cell is completed. Yeah, see this one. Amal, listen, all of you. So here we have cube. First let me explain for this cube. Now we have a lattice point here. Somewhere I explained, I hope you remember. Okay, here is a lattice point. Generally, if you want to get the total crystal, total solid, you will place one more cube here. You place one more cube backside and here one more backside. Total 4. On that 4 you will keep another 4. That's why the atom in the middle is shared by how many? 8. That's why what is the sharing of each point? 1/8. That's good. So the sharing is 1/8. Like that, how many are there? 8. 8 are there na? 8 are there. Sharing is total. So 1 lattice point per unit cell. Is it a primitive? Yes. That's why simple cubic is represented by a letter P. P for primitive. Simple cubic is a primitive. That's why it is a P. Clear? Next one. Ready? So here the sharing is what? In the middle if you place one atom here, that atom cannot be shared by anybody else. That's why this sharing is what? That's why come on say 8 into 1/8 plus 1. How much? Number of lattice points per unit cell. Is it a primitive? No, it's a BCC. It's a BCC and this is what? Simple cube. BCC, it is represented by I. It is represented by I. In Bravais lattice structures, if you have I letter is what? BCC. P letter is what? Simple cubic. Next, FCC. I think you know these points you know already. Sharing. But if a point on the side, it will be shared by another cube. Total how many? Sharing is 1/2. Now, 8 into 1/8 plus 6 into how much? Number of lattice points per unit cell in FCC? 4. That's why this is called capital F. FCC is represented by capital F. So, P, I, F. Now what is this? Base centered. Base centered. Okay. So, here the sharing is what? 1/8. Here the sharing is what? That's why 8 into 1/8 plus 2 into 1/2. Answer. So this is called base center. Base center, which is represented by C letter. Which letter? C. Base center is C. So in Bravais lattice structures, we will be having P, I, F, C. Either P or I or F or C. P for primitive, simple cubic. BCC, I. FCC, BCC B కాదు. BCC, I. FCC, F. Base center, C. Okay, come on. So in all these only one primitive. What is that? Simple cubic. Just finish it. Discuss one beautiful. Actually Amazon servers, whether you use or not, it will charge. That's why there is an option. We can shut down the server, then they won't charge. Generally the server will on for 4 o'clock, evening 4 o'clock. I forgot that actually. Just today I again on that. We will write a simple program to on automatically. It's late for 10 minutes today. Come on. So I hope you are getting the terminology also. Get ready. So primitive, P for primitive, that's why simple cubic is primitive. BCC is represented by I, FCC F, base centered C. Sorry. Ready? Right. So here I have given a small task. Now please identify which are primitive and which are non-primitive. Just see first, all of you. Now, this yellow is a primitive or non-primitive? Huh? Why? How many points are there? If you assume this entire space is filled by these squares, each point is shared by another 4 squares. Here, here, here. That's why sharing is 1 by 4 into 4. That's why 1. Is it a primitive? P for primitive. Next. Is it a primitive cell? Say yes or no? If you assume this entire space is filled by this shape, same tile we can place na. So is it a primitive? Yes. Whenever you are thinking about this, forget others. I can't draw one diagram for each shape. Understand? That's why. Come to this. Because here also 4 are there, sharing 1. Here 4 are there, sharing. Answer. Primitive? Primitive. Now come to this. Here how many points are there? 4. Sharing equal to 1. But in the middle, 1 more is there. That's why number of lattice points per unit cell. Number of lattice points per unit cell. How much? So that's why is it a primitive or non-primitive? Non-primitive, NP. Now come to that. Primitive or non-primitive? Huh? Primitive. In your BSc, you studied like this? Primitive cell which contains lattice points at each corners. You studied this or not, say? At each corner there exists one lattice point. If you see some YouTube videos, they will say this also. At each corner, if there is a lattice point, then it is called a unit cell, primitive cell. Primitive cell, but all primitive cells need not to be like that. Primitive cell, we can say at each corner, if you have a lattice point, that is also each corner you have one lattice point only. So, but here each corner you have, but extra is there, that is why it is not a primitive. Yeah, some people will say that a definition also. Now tell me, is it a primitive or non-primitive? Primitive. Pakka. Why? Oh, only one lattice point. That is why you are saying it is a primitive. Anybody knows what is the special name for that? One name is there for that. Wigner-Seitz cell. Listen, very important. All of you please listen. Wigner-Seitz cell. What is this Wigner-Seitz cell? Wigner-Seitz cell is not so much important in a real space. Sir, what is a real space? If I take XYZ axis, real space, then what is the reciprocal space? If I take a Kx, Ky, Kz, it is the reciprocal space. But in case of reciprocal space, this Wigner-Seitz cell is very crucial. Why? The Wigner-Seitz cell in the reciprocal lattice is called first Brillouin zone. If you understand what is a Wigner-Seitz cell, then only you will understand what is Brillouin zone. Not simply Brillouin zone, first Brillouin zone. So what is this Wigner-Seitz cell and how to construct this? Are you ready? I will explain first real space Wigner-Seitz cell, then after that immediately I will go to the Brillouin zones. Because if you listen the same concept here, then you will understand, visualize how the Brillouin zones will be there in the reciprocal lattice, because we cannot see, we can see only real space, x-axis, y-axis, z-axis we can see, but kx, ky, kz we can't see. Okay, ready? Are you ready? Now the thing is, what is Wigner-Seitz cell? What is a Wigner-Seitz cell? First you want to draw this first? You want to listen? Oh, listen. What is a Wigner-Seitz cell? Again, I am going to take a rangoli. So let me take this. Listen carefully. It's a very crucial. I am not only explaining Wigner-Seitz cell, at the same time I am explaining the Brillouin zone also. Then you will get a clear picture. I have taken a lattice like this, and I am taking a point here. I have chosen a lattice point. This is my lattice point now. Could you please tell me, for this lattice point, what are the first nearest neighbors? I am asking first nearest neighbors. Ready? I think this is 1, 1, 2. And the first nearest and 1. This is also first nearest. This is also. So, I have chosen a lattice point, and after that I have taken the first nearest neighbors. First nearest neighbors. Just I join these lines. Just imaginary, just I dotted lines. Right. Okay. So I have chosen a lattice point, and after that I have taken first nearest neighbors, your roommates only. Okay. Just I join those roommates. Go on. After that I am taking perpendicular bisectors. Perpendicular. Okay. Is it a perpendicular bisector? Now I am taking a perpendicular bisector to the line joining, perpendicular bisector of a line joining a given lattice point and its first nearest neighbors. Over. So, I have chosen a lattice point, I have taken first nearest neighbors, and now I have taken perpendicular bisectors to line joining a given lattice point and first nearest neighbors. Then a region of space is enclosed or not? The region of space enclosed by perpendicular bisectors drawn to lines joining a given lattice point and first nearest neighbors is called Wigner-Seitz cell. That's why in the middle you are having only one lattice point. What physically this Wigner-Seitz cell is? The Wigner-Seitz cell gives you the region of space which is closer to a given lattice point. That is the region of space which is closer to a given lattice point. For example, I have given a lattice point. I am asking, please tell me what is the closer region to that lattice point. Then that Wigner-Seitz cell is nothing but the closer region of space to a given lattice point. How to construct means? I said closer. That's why I have to take first nearest neighbors. And just take the perpendicular bisectors. And the region enclosed by that perpendicular bisectors is nothing but Wigner-Seitz. Wait a minute. Everybody understand this? This is a Wigner-Seitz cell in a real space. Which space we have taken here? A real space. So, Wigner-Seitz cell story is khatam here, over for the real space. But if you take all these points in the reciprocal lattice, the Wigner-Seitz cell in reciprocal lattice is called first Brillouin zone. Sir, why you are saying first Brillouin zone, sir? First nearest neighbors I have taken. That's why it is called first Brillouin zone. Sir, if I take second nearest neighbors, shall I get the second Brillouin zone? Yes, see. Ready? Now this is my given lattice point. Now I am going to take the second nearest neighbors. I hope everybody know, is it a second nearest? Now again I am joining Babu. Now I am in the reciprocal space. I am just extending this. Now I join the second nearest neighbors. Then what I have to take? Perpendicular bisectors. I am taking yellow color. Okay. Line and perpendicular bisectors. Okay. So now, could you please tell me what is a white line? First, now this is the reciprocal lattice. Just assume reciprocal lattice. What is that white color line? First boundary. First Brillouin zone. That is called Bragg plane. White color lines are called first Bragg planes. That yellow color lines are called second Bragg plane. The region enclosed between first Bragg plane and second Bragg plane is called second Brillouin zone. That's what I mean. See, the region of space enclosed between only white and yellow. Cross the first Bragg plane and don't cross the second Bragg plane. That region is called second Brillouin zone. Third Brillouin zone. Cross the second Bragg plane don't cross the third Bragg plane. That's it. Let us see, that also will extend. It's a nice, beautiful. I think this is 3, 3, this is also 3, and this also 3. Now ready, don't get tension. Okay, now I am taking, this is the line. I hope now you understand. Oh, I will take the another color. Pink color line. That pink or orange? Huh? Orange. Sorry, orange color. I hope you are observing. Now, where is the third Brillouin zone? Identify. I told you, cross the second Bragg plane, but don't cross the third Bragg plane. Second Bragg plane is yellow, and that orange is the third one. Come on, I say. Cross the yellow, don't cross orange. Cross the yellow, but don't cross the orange. Cross the yellow, but don't cross that orange. Cross the yellow, but don't cross the orange. Like this, if you imagine any crystal in the reciprocal space, how this crystal structure will be in the reciprocal space? This is the combination of Brillouin zones. In the middle, you are having a first Brillouin zone. Sir, first Brillouin zone, it should be there, but in the middle, I think this is the reciprocal lattice. In the middle, we are having a first Brillouin zone. That is surrounded by second Brillouin zone. That is surrounded by, like that, it is a simply combination of all Brillouin zones. Now, you are sending an X-ray beam. Now that X-ray beam will enter into the crystal. It enters up to second Bragg plane and reflected. That is called second order diffraction. So it is interacting with the second Brillouin zone. If it is reflected back from the third Brillouin zone, we will say third order diffraction. So that order of diffraction or reflection will be given by these Brillouin zones only. But all these things we should not discuss in the real space. Real space we have to discuss only Wigner-Seitz cell. If you imagine the same diagram in the reciprocal space, then the Wigner-Seitz cell in the reciprocal space is called first Brillouin zone, because we have taken first nearest neighbors. If you extend this to the second nearest, third nearest, fourth nearest, then we will get first Brillouin zone surrounded by second Brillouin zone, surrounded by third, so like that. So what are these Brillouin zones means, which will tell you about the diffraction order. It interacts with the second and reflected back. That is called second order, third order, like that. Is that clear? Come on. actually Bragg line in 2 dimension. In 3 dimension we call it as a Bragg plane. Or perpendicular bisectors are called Bragg planes in reciprocal lattice. Again we will get back to this. We will discuss what is reciprocal lattice. See, today please read Wigner-Seitz cell, that is in the beginning, but immediately go on to read first Brillouin zone. That is where it is, I think it is in the reciprocal lattice, X-ray diffraction, before X-ray diffraction. Just if you read, you will understand what is the similarities between those. Then while I am explaining Brillouin zones, you won't get any difficulty there. Whether you understand or not, please read the book. Whether you understand or not does not matter, just read the book and come to the class next. I request everybody, please download the Wahab book, SSP, and read. Just after the class, 1 hour, please read. Don't go to the room. If you go to the room, you will sleep. The region enclosed by perpendicular bisectors is called Wigner-Seitz cell. One more point you have to add. This is the region of space which is closer which is closer to a given lattice point, to a given lattice point. Please write that also. Now the last one. Bravais lattice structure. It's not a Bravais, it's a Bravais. Bravais. I think just write those lines. I think you can draw it later also. Just write those points. I think first point is not required, I think. Draw perpendiculars to the lines joining first nearest neighbors and given lattice point. That is enough, I think. And the region enclosed by that perpendicular bisectors is nothing but perpendicular bisectors. Sorry. Or if you see the textbook and write, their language is good, better than me. Are you ready? Can you draw this later? Everybody? Otherwise, after the explanation, if you want, you can draw it. Now see. Bravais lattice structure. All lattice structures are not Bravais lattice structures. Then what is the speciality of Bravais lattice? For example, if you consider a student in this classroom, that student is surrounded by what? Students only. Say yes or no? And one lattice point is having same environment. That type of lattice structure is called Bravais lattice structure. 1 minute. This is, we can say identical, or we can say lattice points are, all lattice points are identical. All lattice points are equivalent. I think this word is better than that. Equivalent. 1 minute. All lattice points are equivalent. That means every lattice point is having the same environment as others. Every lattice point is having same environment as others. That also, if you want, you can write. Every lattice point has the same environment as others. Now wait a minute, Babu. Now I am taking 3-dimensional Bravais lattice structures. Okay, so for this first I have to take the 3-dimensional axis. Okay, so this is the x-axis and y and z. So this is alpha, opposite to y beta, opposite to z gamma. That alpha plus beta plus gamma equal to how much? Alpha plus beta plus gamma is not 360. Go to that corner of your room, corner of the room. Okay, how much on the floor? 90. How much on that wall? 90. How much on this wall? 90. Total remaining 90 gone to other ni bonda. Sum of all angles at a point in a plane is 360. These are 3 angles in a different planes. One is in the xy plane, another is in the yz plane, another is in the Z. If anybody asks, a student asks, sir, alpha plus beta plus gamma is not 360, what is the reason? Sum of all the angles at a point in a plane is 360. In a plane is 360. Different planes angle sum is not 360. Understand? Good. Now ready. So here I am taking the method called symmetry breaking. Symmetry breaking. I don't know how you remembered these structures in your MSc. Our sir explained this. Gauri Shankar Singh, our sir, CMP sir. Okay. Sir explained very beautifully. I like this method. So this is not in the books. Listen. Symmetry breaking he has taken. Easy to understand. Easy to read. So here we are having parameters A, B and C. A, B, C are lattice parameters. Alpha, beta, gamma are the angles. Symmetry breaking. First, sir taken full symmetry. Full symmetry means A equal to B equal to C. All are same. And angles also alpha equal to beta equal to gamma, all are equal to 90. This is called full symmetric system. Good. After that, breaking the symmetry. I am not changing the angle symmetry. That's why angle symmetry as it is. I hope you are observing. Alpha equal to beta equal to gamma equal to 90. I am not spoiling the angle symmetry. Now I am disturbing this symmetry, sides symmetry. Ready? Here A equal to B equal to C. Now break the symmetry. A equal to B. Again break. Next, I request you please write this 3 again. Means A equal to B equal to C. Now for this I am going to take breaking the angle symmetry. Are you ready? Right. Now I am breaking this angle symmetry. Alpha equal to beta equal to gamma but not equal to 90. Symmetry gone. Next, alpha equal to beta equal to 90 but gamma equal to, again symmetry gone. Next, here third one, any two angles are 90 amma. Any two angles are 90. One student will argue with me, textbooks are given alpha, gamma. That alpha, gamma, na beta, it depends upon where you are taking the axis. It's not fixed. Any two angles are 90, third angle is less than 120. We are always stick to the textbooks only. We forgot to think about our originality. Whatever it is given, we will believe that only. Any angle. So I can change now. You have taken one coordinate system, I can change my coordinate system. But textbooks will give like this. Okay, alpha equal to gamma equal to 90. Anything you can take, one more time I am saying. Okay, and what is the other one? Beta. Beta less than 120 but not equal to 90. I repeat. See, once again angle symmetry breaking. Alpha, beta, gamma all are same. Now we are breaking the first one. Alpha, beta, gamma same but not equal to 90. Next, alpha, beta 90, gamma 120. Next, alpha, gamma, any two angles 90, beta less than 120. Because you said less than 120, it may be 90 now, but it is not equal to. Why? It is less than 120, equal to 90, again symmetry. Understand? That's it. And I started with the full symmetry, now I am ending with the no symmetry. I started my journey with A equal to B equal to C, alpha equal to beta equal to gamma equal to 90. I end with A is not equal to B is not equal to C, alpha not equal to beta not equal to 90, not equal to 90. Only you have to remember this. This is very easy. So, alpha equal to beta equal to gamma but not equal to 90. Next, alpha equal to beta equal to 90. Next, alpha equal to gamma equal to 90, beta less than 120 not equal to 90. Next, alpha not equal to beta not equal to gamma not equal to 90. Full asymmetry, there is no symmetry at all. After that, I will tell you a small technique. This is my technique to remember. Sir given this and I added something to this. Just remember this. C, T, O, R, HMT. I don't know how many of you know this. Do you know HMT watches are there earlier? Hindustan Machine Tools. Huh? Okay. Where it is? Where it is? It is Hyderabad. But now it is not there, it's closed. Okay. CT, OR, HM. Say? CT, OR, HMT. Once again. CT, OR, HMT. Let us say CT company watch, HMT company watch. అత్తగారు సిటీ కంపెనీ కానీ హెచ్ఎంటీ వాచ్ కానీ పెట్టాలి, లేదంటే పెళ్లి చేసుకోరు. అంతేనా? అర్థం కాలేదా? ఏం పర్లేదు చూడు. రెడీయా? సో C for cubic, T for tetragonal. Once again, CTOR HMT. Say CTOR HMT. Now ready. C T tetragonal, O orthorhombic, O orthorhombic, R rhombohedral, H hexagonal, M monoclinic, T triclinic. Ready? C T O R H M T. అంతే. రైటా? Rhombohedral, one more name is there, but why I have taken R, it is easy. CTR HMT, CTORR, CTORR HMT. R another name is a trigonal. Rhombohedral another name. Symmetry breaking, and that's it. And I am giving a small homework. You please write the Bravais lattice vectors for Bravais lattice structures for 2D. This is your homework. How many will be there? 5 structures will be there. Here in 3D how many? 14. 7 కాదు, 14. అంటే 7 2s are 14 కాదు. Earlier I said na PIFC. I will write it, don't worry. I told you earlier, P for simple cubic, I for BCC, C for base center, F for, yes. See, base center exists only for A is not equal to B is not equal to C. A is not equal to B is not equal to C. So like this, total 14. So this is your homework. Do for 2D. Please practice. Don't simply write that symmetry. You please practice. You will remember. Endama 2, 4, 8, 9, 10, 12, 13. One more is there. Here maybe C. Here no. Huh? Oh, F. Sir. Yeah, F. Simple cubic base and simple cubic BCC FCC. Break the symmetry. First take full symmetry in angles and break the symmetry in the sides. Next again copy paste that sides and next break the symmetry in the angles. Textbook order is not this, but this is the better order to remember. If you become a teacher, please always remember, we are not copy paste of textbooks. Always, but you should not teach wrong one, but we should not teach the same thing in the textbooks. It's a reference, that's it.